طابعني عزيز أم كاتتان باش بابتي أمرومان بريتيلا chapter 2 ل introduction to solid state physics chapter 2 لسر crystal structure دبراوي زورة بابتك كردوما بدو بشاوة chapter 2 crystal structure A أمرو وردقرين ودرسي دهاتو chapter 2 crystal structure B وردقرين. Today's subject is chapter 2 crystal structure part A in the subject of Introduction to Solid-State Physics. Crystal structure of a metal can be described in terms of its unit cell. The unit cell is a small box containing one or more atoms arranged in 3 dimensions. The unit cell stacked in 3-dimensional space describe the arrangement of atoms of the crystal. The unit cell is represented in terms of its lattice parameters, which are the length of the cell each, A, B, and C, and the angles between them, alpha, beta, and gamma. The position of the atoms inside the unit cell are described by the set of atomic positions xi, yi, and zi, measured from lattice point. Ideal crystal. An ideal crystal is a periodic array of structural units such as atoms or molecules. It can be constructed by the infinite repetition of these identical structural units in space. Structure can be described in terms of a lattice with a group of atoms attached to each lattice point. The group of atoms is the basis. This graph or figure shows the atoms in a crystal structure. 2 types of atoms exist, so it's a compound. Bravier's lattice, a finite array of discrete points with an arrangement and orientation that appears exactly the same from any of the points the array is viewed from. A Bravier's lattice consists of all points with position vectors R of the form R n1a1 plus n2a2 plus n3a3. The expansion coefficients n1, n2, and a3 must be integers, while the vectors a1, a2, and 3 are primitive vectors. Primitive unit cell. A primitive cell or primitive unit cell is a volume space that when translated through all the vectors in a Bravier's lattice just fills all of spaces without either overlapping itself or leaving voids. A primitive cell must contain precisely 1 lattice point. This is a unit cell, can be said. This box inside this crystal structure in the 2 graphs or the 2 figures is a unit cell. Unit cell, the smallest portion of a crystal lattice is called unit cell. By repeating in different directions, unit cell generates the entire lattice. Parameters of a unit cell. A unit cell is characterized by 6 parameters. These parameters are 3H, A, B, and C, and angles between them, alpha, beta, and gamma. Dimensions along the edge of a unit cell is represented by A, B, and C. Edge of unit cell may or may not be mutually perpendicular. The angles between B and C is represented by alpha, between A and C by beta, and between A and B by gamma. Types of unit cell. There are 2 types of unit cells, primitive and centered unit cells. Primitive unit cell, when particles in unit cell are present only at the corners, it's called the primitive unit cell. Centered unit cell, when particles are present at other positions in addition to those at corners in a unit cell, it is called centered unit cell. There are 3 types of centered unit cell. A, body-centered unit cell. If one constituent particle lies at the center of the body of a unit cell, in addition to the particles lying at the corners, it is called body-centered unit cell. B, face-centered unit cell. If one constituent particles lie at the center of each face, beside the particles lying at the corner, it's called a face-centered unit cell. And centered unit cell, if one constituent particle lies at the center of any 2 opposite faces beside the particles lying at the corners, it is known as end-centered unit cell. It's also known as base centered unit cell. Fundamental types of lattice. Crystal lattice can be mapped into themselves by lattice translation T and by various other symmetry operations. A typical symmetry operation is that of rotation about an axis that passes through a lattice point. Allowed rotations of lattice are 2 pi, 2 pi by 2, 2 pi by 3, 2 pi by 4, 2 pi by 6. Lattice parameters and crystal system. Lattice parameters are length of the three sides, A, B, and C, and angles between the sides, alpha, beta, gamma, which can be seen that here, this one, A, and this side, B, and this side, C, and the angles alpha, beta, gamma in this unit cell can be clearly seen. Also here in the parameters, also in this box, which is a unit cell. There are 7 unique crystal systems: cubic, isometric, 2 hexagonal, 3 tetragonal, 4 rhombohedral, trigonal, orthorhombic, monoclinic, and triclinic crystal systems. Lattice parameters, as we say, the lattice parameters are the lengths A, B, and C, and the angles between them, alpha, beta, and gamma. 14 Brevis lattices in 3 dimensions. The 14 possible Brevis lattices are as shown in these figures. Cubic, in the cubic, these are cubic Brevis lattices, crystal structure. Here, A, B, and C are equal, and alpha, beta, gamma angles are also equal and equal to 90 degrees. Tetragonal, in these 2 figures can be seen, A equal to B and not equal to C, while alpha, beta, and gamma are all equal to 90 degrees. Orthorhombic, these figures, 4 figures, P, I, F, C, A not equal to B and not equal to C. Alpha, beta, and gamma, the angles are all equal and all equal to 90 degrees. Hexagonal, in this figure, A equal to B and not equal to C. Alpha and beta are equal to 90 degrees, while gamma equal to 120 degrees. Trigonal, A and B and C are equal, alpha equal to B and equal to gamma, but they are not equal to 90 degrees. Monoclinic, A not equal to B, not equal to C. Alpha and gamma are equal to 90 degrees, while beta is not equal to 120 degrees in these 2 figures. Triclinic, A and B and C are not equal, alpha, beta, gamma are not equal, and they are not equal to 90 degrees. 4 types of unit cell, P, here, the symbols here, P, primitive, I, body center, F, face center, C, side center, 7 crystal classes, 14 Brevis lattices. So we have 4 types of unit cell: primitive, body-centered, face-centered, and side-centered. While crystal classes are, we have 7 crystal classes, and the total Brevis lattices are 14. This is also another figure of crystal lattice, can be seen primitive or simple, face-centered, and this is a primitive or simple, and this is a body-centered. At the corners, we have atoms at the corner, and at the center, body center, here we have another atom. Here, face center, we have 8 atoms at the corners, and each face has, at the center of each face, also we have another atom. So that's why it's called face center. This is also a primitive. Tetragonal lattice, there are 2 possible types of tetragonal lattice, primitive and body-centered unit cell. In these lattices, one side is different in length and angles between faces, and between faces are equal to 90 degrees, as shown in this is primitive and body-centered. Orthorhombic lattice, 4 types of orthorhombic lattice are possible. They are primitive, head-centered, end-centered, body-centered, and face-centered. They have unequal sides. The angles between their faces are equal to 90 degrees. 4 types of orthorhombic: primitive, head-centered, body-centered, and face-centered, and the sides are not equal. While monoclinic, there are 2 possible types of monoclinics. They are primitive and end-centered. They have unequal sides and 2 faces have angles other than 90 degrees. The sides are not equal and they have two angles other than 90 degrees, as shown in these 2 figures. Hexagonal is one of one type only. It has one side is different in length to the other 2, and angles on 2 faces are 60 degrees. Hexagonal. Rhombohedral lattice, only one type of lattice is possible for rhombohedral lattice. It has all sides equal and angles on 2 faces are less than 90 degrees. Triclinic lattice has only one type of lattice. It has unequal side and none of the angles between faces are equal to 90. Triclinic lattice. Number of atoms in a unit cell. A crystal lattice is made of very large number of unit cells, and lattice points are the representation of constituents. Therefore, the number of atoms in a unit cell of a crystal lattice can be calculated. Number of atoms in a primitive cubic unit cell. In primitive unit cell, atoms are present at corners only. In a crystal lattice, every corner is shared by 8 adjacent unit cells. Therefore, only 1/8 of an atom or other constant particles belong to a particular unit cell. Therefore, since there are 8 atoms present in a unit cell on every corner, therefore the total number of atoms in one unit cell equal to 8 divided by 8 becomes 1 atom only. Thus, 1 atom is present in a primitive cubic unit cell. Body-centered BCC unit cell. There are 8 atoms at each corner and 1 atom present at the center of a body. In a body-centered cubic BCC unit cell, therefore the number of atoms present in a body-centered cubic unit cell is 8 divided by 8 atoms per corner becomes 1 atom. 1 body-centered atoms, 1. So total number of atoms per unit cell in the BCC unit cell is 1 plus 1 equal to 2 atoms. Face-centered cubic FCC unit cell. In a face-centered cubic unit cell, there are 8 atoms present in each corner. A cubic has 6 faces, therefore total 6 atoms are present at the corner, at the center of each face. Each atom present at corners is shared by adjacent 8 atoms, and each atom present at the center of face is shared between adjacent 2 atoms. Therefore, number of atoms in an FCC unit cell is 8 divided by 8 becomes 1. 6 faces centered atoms divided by half, atom per unit cell so become 3. So total number of atoms per unit cell in a face FCC unit cell is 1 plus 3 equal 4 atoms. Cubic or isometric unit cell, another figures, simple. This is a simple previous lattice, 3 previous lattice here. Simple cubic, face-centered cubic, and body-centered cubic. As we mentioned before, in this, the length A, B, and C, A equal to B and equal to C, and alpha, beta, and gamma are all equal to 90 degrees. Simple cubic center, here we can see that cubic center, the atoms are clearly seen. 1 atom per unit cell, so 8 divided by 8 become 1. Face-centered cubic center, FC structure, FCC, exhibits aluminum, Cu, Au, Ag, Ni, platinum. Close packet direction are phase diagonal. Coordination number equal to 12. 4 atoms per unit cell. All atoms are identical. So 6 divided by 2 faces plus 8 divided by 8 corners become 4 atoms adapted from this figure. Body-centered cubic structure BCC exhibits like by C, R, F, E, M, O, T, A, and W. Closed packet direction are cubic diagonals. Coordination number 8. All atoms are identical, so 2 atoms per unit cell available. Which one has most packing in these 3 figures? For that reason, FCC is also referred to as cubic closed packed CCP. Hexagonal, only one Bravais lattice. A equal to B and not equal to C, alpha equal to 120 degree, beta and gamma are equal and equal to 90 degree. This figure shows a hexagonal structure. Hexagonal closed pack structure, SCP. It can be seen A sides, B sides, and C sides exhibited by AB stacking sequences coordination number equal to 2. Two-dimensional projection can be seen here, top layer, middle layer, and bottom layer. It can be clearly seen the hexagonal packed structure. Tetragonal system, 2 Bravais lattice, simple tetragonal and body-centered tetragonal. As we said, A equal to B and not equal to C, alpha, beta, and gamma are all equal and equal to 90 degrees. Trigonal, rhombohedral system, only one Bravais lattice. This is the shape of it. A equal to B, not equal to C, alpha equal to 120 degree, beta and gamma are equal and equal to 90 degree. Orthorhombic, we have 4 Bravais lattices. Simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, and face-centered orthorhombic. In these symmetry elements, A not equal to B not equal to C, while alpha, beta, and gamma are equal and all of them equal to 90 degree. Monoclinic, we have 2 Bravais, that is simple, monoclinic, base-centered monoclinic. A and B and C are different. Alpha and gamma equal to 90 degree, and beta is not equal to 90 degree. Triclinic, only one Bravais lattice shown here. A and B, C are not equal. Alpha, beta, and gamma are not equal, and they are not equal to 90 degree. Layer stacking sequences is hexagonal closed packet, AB repeated, FCC, and ABC repeated in the same way. Thank you very much and wish you all a luck for listening to this valuable lecture. Regards.